All right. I would also like to thank the ICAPS, I guess, governing body or whatever for having this journal track. It was really great, low barrier of entry for me to come in and hang out with you guys from another community. And the ICAPS community is just wonderful, and I would love to come back. So that was whoever thought of that, great idea. I am Michael Otte. This is work that I did with my PhD advisor back when I was at the University of Colorado Boulder. I'm currently at MIT, and my new advisor as a postdoc is Emilio Frizzoli for the last couple of years. So I'm going to talk to you today about a parallelization method for sampling-based motion planning, and we have some interesting speed-up results. So to kind of frame what I mean by sampling-based motion planning, this is the domain that I play in. You're given a space. This is a bounded space in most cases. And you have some set of obstacles within that space, also bounded, each of them a subset of space. You have a point that you start at, a point that you want to get to called the goal, and you want to find a path from the start to the goal. So this is just sampling-based motion planning. You're also provided with a collision detector function, and in the most common form, this will output a binary value, yes or no, either this point or this trajectory between points is in collision or not. Given this information in sampling-based motion planning, we start building a tree either from the start or the goal. I will assume that we start building it from the goal towards the start. We sample a point, we check if we can connect it to the tree or the graph that we're building, and if we can't, then we chuck out that point and we continue. So we just do rejection sampling in the most simple case until we manage to get close enough to the goal that we can connect. And then we have found our path. And this is defined as a subset of points for which the transitions or the trajectories from one to the next are all known to be safe. Finite length in the cardinality of the set of points. Now, I am going to be more interested in shortest path planning. So what is that? Well, we're also given a distance function in this space. And once we find a path, then we're interested in finding actually the best path over the set of all paths. So in sampling-based motion planning, when we're worried about finding the shortest path, we continue sampling after we've found the first path, and we rewire the graph that we've created. And as we sample more and more points, this path gets closer and closer to the optimal path. And in the limit, there's a lot of nice proofs that show that you will actually get the shortest path if you can sample an infinite number of points, at least with probability 1 in a lot of cases. It's worth noting that we're doing the sampling-based thing in practice because our robot, which I've represented here by a piano because the piano mover's problem is the name of the motion planning problem, it lives in some world that we all see. And this is given by some set of coordinates and maybe some rotations and even some articulated joint angles. So these are our dimensions of our state space. And this is the workspace. This is where the robot lives. There's also, separate from that, the configuration space. And the robot's location and joint angles in one place in the workspace, that corresponds to a point in the configuration space. And a different configuration in the workspace corresponds to a different point in the configuration space. And we model the possible, if it's possible to get from one to the other, then this is what the trajectories in the configuration space do. Now, the reason that we distinguish between these two is because we're given obstacles in the workspace, but it's really hard, often, even impossible, to know how these things map into the configuration space. So this is why we have to use sampling to kind of get around them in the first place. Now, it's not always impossible to represent your workspace obstacle in the configuration space, but oftentimes it's just really, really time-consuming to do so. So it's faster just to use these sampling-based motion planning methods anyway in high-dimensional state spaces. So two reasons you use them. One, you have no idea what the obstacles look like. The other is it's just too hard to know what they look like. Now, to get back to what I'm going to tell you about today, which is CFOREST, and it's a way that you can parallelize a lot of different sampling-based motion planning algorithms if you care about finding a shortest path with them. And so if you're given a network of computers and you want to parallelize the computation across those. And it's a very simple idea. And it's instead of using just one tree, we're going to use a forest of trees. We'll start talking about each computer, each CPU in this network, let's say, grows its own tree. But in addition to just doing this OR parallel thing where you just grow a unique tree on each CPU, we're going to let the trees communicate during the search. So I've given them ears and beaks to represent this passing of messages during the search. And the reason you may want to do this is because eventually somebody might find a really good leaf or branch to the leaf, and he thinks it would be great if everybody had that. So he's going to take his branch that's really good, and then you pass that around using message passing, and everybody else inserts that branch into their tree. So this is why it's called CFOREST. It actually stands for something, which I think is really cool. We often call the configuration space the C space, so this is like really cool. A coupled forest of random engrafting search trees. I was really happy to find the word engrafting existed, and it means cutting off a branch and putting it onto another tree. So it's just kind of like very serendipitous that this whole acronym worked out. I'm really happy about that. This is just parallelizing these trees that some other algorithm is running lower. So this is kind of a meta algorithm. Whatever properties your trees have, the forest will inherit those properties. So I've used the tree with the happy, special branch as a metaphor for this planning thing. For the rest of the talk, I'm going to be using this also. So these are all equivalent here in this talk, these different pictures. And I'm going to be talking about a robot that wants to get to a goal. There's the robot in the middle there. The tower is the goal, and he's found a good path here. So why is it good to share these things in practice? Well, let's assume that each of these is generated on its own CPU. They're each building their own random tree here. Now, the red all the way on the left has found a shortest path. If you're using just one computer by itself, you can have a nice heuristic where we don't need to worry about sampling any point that it would take longer to get from the start to that point, and then from that point to the goal. If that is longer than the length of the current path, then we can immediately chuck it out. So if our space obeys the triangle inequality, then this defines a nice subregion of the space that we can sample within in the future. And we also can prune everything that's outside of that space, because it can't possibly help us find any better paths. In Euclidean space, this defines an ellipsoid. I don't know, when I was a kid, you put two pins into the wall and you put some string on it, so that's our best path length, and you can take like a marker and make a nice ellipse using that. That's exactly what this is doing. So if he shares this information with everybody else, they can also prune and stop sampling outside of that ellipse. Another reason that this is very helpful is because there is some probability that you will find a better path based on the current way that your nodes are in the configuration space. An omniscient being would know that if we sampled within these shaded regions, we would immediately find a better path. The algorithm, of course, doesn't know that. If it did, it would exploit it, and you'd find paths much quicker. But by sharing this good branch, we allow everybody else to also be able to sample from the good part of the configuration space that will result in an even better path. So it's these two things that sharing this good branch among all of the CPUs allows us to do. Then maybe now the middle CPU can capitalize on that information from the red CPU, and he finds an even better path. He'll share that with everybody else, and you can see how this kind of thing, everybody tends to help everybody else out. Now, quick word on speed up and efficiency when we're talking about parallelizing code. Let C be the number of CPUs. The time to solve a particular problem with one CPU is time sub 1. The time to solve the exact same problem with C CPUs is time sub C. So the speed up is then calculated as time sub 1 divided by time sub C. Just how much faster can we solve this problem on the network of CPUs than we could on a single CPU. And efficiency is to take that value then and divide it by the number of computers in our CPU. So it kind of represents like how much power do we actually need to solve this problem. The experiments that I do, I compare to this OR parallel idea where we just build a single tree on each CPU. There's a couple of different environments that I've used: manipulator arm, a toy problem with multi-robot planner, office environment with 4 different robots, and the alpha benchmark problem, which everybody I'm sure is familiar with. The search algorithms that I've done is RRT star, which is, as of a couple of years ago, at least state-of-the-art sampling-based motion planning algorithm. Log of n per iteration, it keeps an inconsistent graph. I also compare it to something from my PhD thesis, which took longer per iteration but maintained a consistent graph, just to show that this parallelization method works in a bunch of different settings. So here is the results of the arm thing for RRT star, and the warmer colors correspond to shorter paths. So I'm defining, like, I want to find a path that's at least a certain amount good, and that's what the numbers mean. So the warmers are harder to find. And now this is OR parallel. The dotted line here shows linear speedup. So it is super linear on the very easiest problem, which is kind of nice. And you do get speedup, right? The more CPUs you have with OR parallel, the better it is. But when we allow communication between these things, we find that we end up getting a lot better speedup. In fact, it's super linear in a lot of cases. And I won't dwell on that, but we can look at efficiency too. So we see that, like, all right, efficiencies of 3 versus efficiencies less than 1 for the OR parallel. I don't have tons of time, but the results for all of these were very good. The results compared to OR parallel for the alpha problem were not so hot. And the reason for this is because until we find that first solution, we can't use these heuristics for anything. And so we're essentially running OR parallel until we find the first solution. Whenever it takes most of the time to find the first solution, then it doesn't make any difference what happens after that. And that's essentially these results. We don't break the laws of thermodynamics because we can do the same thing on a single CPU, and we find that we also get really good speedup, kind of similar results. If you want to know more about that, I'll talk to you later. And in conclusion, I've told you about a way to parallelize shortest path planning algorithms in the sampling-based domain. Hopefully I've given you some intuition why it works. You have these heuristics that work really well and parallel to each other. Somebody finds some information, they can share it with everybody else, and that makes everybody else's life easier. I'm a big fan of that sort of thing for parallelization. It works really well with shortest path planning, not very well with feasible path planning, and not very well when the first solution takes most of your planning time. If you can find like a suboptimal solution very quickly, you can capitalize on that to find a more optimal solution more quickly using this method, so you should do that. The results are in IEEE Transactions on Robotics in 13. The SPRT results I put in the extended abstract for this conference, so slightly different work in either one. And all of this stuff is from my PhD thesis, which is a couple of years old now. Anyhow, that is it, and I would love to take any questions that you have.
So we have time for maybe 1 or 2 questions? Yeah.
Rob gets to go first since you're closer. Would there be any advantage to having some of these go the other way? Like you've got them all going in the same direction from goal to start. If you had half of them going the other way, could you do some more powerful sharing?
I think that is totally possible, right? Like bidirectional search helps you in a lot of situations. And so like if there was some bottleneck that was very hard for one to get out of, but it was very easy to get like into that area, then one would be able to find that and share it with everybody else, and then they'd be able to use it. So yeah, definitely. If you can somehow find some other way, maybe everybody is doing a slightly different planning type even and sharing the results. Like maybe you don't know which one will work really better in one particular environment, but as soon as somebody finds one, then it'll benefit everybody else. Like all of that stuff is like really interesting ideas, and I probably don't have time myself to do it. This is a couple of years old and I'm going off another direction. So if anybody want to pick up the ball on here and do like cool work on it, like feel free, just like, cite me and let me know that you did it.
So this speedup sounds really, well, it works well, as you demonstrated. But it seems like dividing this search space over the CPUs in this way, it seems like there's a lot of redundant, maybe, computations going on in the same area. So what's I would say the typical intuition is to divide the area over the CPUs and let each of them find a solution for that separate part of the path. So why not do that? Why would this be better?
So that's a great question, and there is related work that has looked at parallelizing the search by doing it separately in each part of the space and then kind of figuring out how to mortar those things together. I guess with that, the most speed up that you can hope for is kind of linear speed up. So the fact that we have super linear speed up here is kind of interesting. Maybe that's a little too provocative thing for me to say. I'm sure that you could think of an example where the other thing would also have super linear speed up. So I'm now backpedaling on that. But I think that it might be even better to do both kind of in parallel, where you have like multiple CPUs growing from multiple different regions. One of the problems is tying these things together if you started from different places, and the heuristic relies on the fact that you know the length of the shortest path, or that you can extract that shortest path. So that will require like additional overhead in that case. But I can't really comment on if it will be better or worse or anything. I think you really have to do the experiments. It'll probably be environment dependent.